you should see that then we have all but stated the fundamental theorem in terms of the depth function. Now here's a more formal statement of the fundamental theorem of calculus. Fundamental theorem says that if big F prime of x equals little f of x, then when we integrate little f of x from x equals a to x equals b, we get the difference in value of big F between a and b. That is, little f of x, of course, is the rate at which big F changes. So by integrating the rate, by summing up the average rates times the x intervals, we get the change in the big function, of which this is the rate. The function big F of x, of which this is the rate. Big F is your quantity function, little f is your rate function, and this is nothing but a statement of that fact. We say that f of x is an antiderivative of little f of x. Big F is an antiderivative of little f. Okay? Little f has infinitely many antiderivatives because you can always add a constant number to your big F and still get little f as the derivative, right? The constant number has 0 as its derivative. However, that wouldn't matter. If you added the same constant to big F both here and here, the constant would subtract off and would have no effect on this result. Let's do an example. Let's suppose that the rate of depth change is r of t equals 2t minus 3. Okay, what's the depth change from clock time t equals 2 to t equals 5? Well, this is a linear rate function. So the area is just going to be the average rate times delta t. Now what's the average rate? Well, if we plug in t equals 2 into r of t equals 2t minus 3, we get a rate of 1. So the altitude of this graph would be 1 here. Plugging in 5, we get 7. So the rate goes from 5 to 7. If we think of this as a depth change rate in centimeters per second, the depth change rate goes from 1 centimeter per second to 7 centimeters per second. I think I might have said something about 5 to 7 a minute ago, and if I did, please disregard it. It's 1 centimeter per second to 5 to 7 centimeters per second. The average between 1 and 7 is, of course, 4. So that the average rate is 4. If you want to think centimeters per second, that's fine. And from t equals 2 to t equals 5, your delta t is, of course, 3. You might think 3 seconds. So an average of 4 centimeters per second for 3 seconds gives us a depth change of 12 centimeters. The area is the integral from 2 to 5 of 2t minus 3 dt. That is how we write the area under this graph. Now the question is, does that integral actually come out to be 12? We can see that the integral does come out to be 12 if we use the fundamental theorem of calculus. Remember, this integral is going to be sum f of 5 minus sum f of 2, where f is an antiderivative of 2t minus 3. That is, 2t minus 3 is a derivative of the f function. Well, what would the f function be? What's an antiderivative of 2t minus 3? This is a linear function. The antiderivative is going to be a quadratic function, and the simplest one to use is t squared minus 3t. Obviously, the derivative of t squared is 2t. Derivative of negative 3t is negative 3. So we're going to say now that the integral is just f of 5 minus f of 2. Well, we said a minute ago that the area under that curve had to be 12. What's f of 5? Plug in 5, t squared is 25, 3t is 15, 25 minus 15 is 10. Plug in 2, we have 4 minus 6, or negative 2. 10 minus negative 2 is 12. So the fundamental theorem of calculus gives us the same result that common sense with the average rate of a linear function gave us.